Good afternoon, everyone. It's time for us to begin our part 2 of common Wi-Fi problems. Last month, we looked at 5 common Wi-Fi problems and really looked at them theoretically. We're going to get a little more practical this month and talk about some of the practical implications of these problems, the causes of the problems, and of course, some of the troubleshooting tips and techniques we might use. We are in the process right now at CWNP of updating the CWAP certification. And in the past, the certification has been much about simply learning how to use a protocol and spectrum analyzer and learning the details of frames and basic wireless LAN communications. Well, the goal is to take that and still look at that knowledge, but also really focus on the troubleshooting side. So CWAP is becoming a troubleshooting masterclass and certification for those that work in the wireless industry. And so over the last couple of months, we've been looking at some things related to wireless analysis and troubleshooting. And next month, we'll be looking at network troubleshooting in general. So we're going to be talking about some troubleshooting methodology next month and some of the basic processes we use to troubleshoot networks. That's, of course, wireless networks, but also wired networks. And so we'll be going through that next month in a webinar. And then the following month, we'll be looking at what's new in CWAP. So as we're in the release month, we'll be looking at how the certification has changed from the perspective of objectives and what's covered in our courses, study guides, and on the exam. So today, we're on part 2 of our common Wi-Fi problems. And before we get into the agenda for today, we'll first get a brief overview of the CWNP certifications as we typically do. Now, let me just point out that we just released a video a week or so ago, and you can see it on our YouTube channel, CWNP TV, and it will eventually also be at the website on the certifications page that gives an overview of the primary certification track that most people go through, which is CWNA, and then the professional level, CWSP, CWDP, and CWAP, and finally CWNE. So it gives you an overview of these different certifications, what is involved in them, and what they cover and who they're good for and that kind of thing. So it's a great little 4.5 or so minute video that gives you a nice overview of the certifications. But we do start with the CWNA, and the CWNA is the foundation for those that want to actually move through our certifications and gain either professional or expert level status. With CWNA, you lay the foundation that is really essential understanding to prepare for CWSP, CWDP, CWAP, and so forth. So that is very important. CWNA is required for CWSP, CWDP, and CWAP. So you have to have your CWNA first before those certifications can be acquired. And before you can become a CWNE, you have to have all 4 of the other certifications on this screen. In addition, CWNEs go through a process of being validated by a board of advisors. And that board of advisors consists of 5 different CWNEs who look at the application and determine the worthiness for the credential. So we do help you along the way. The application itself tells you clearly what the qualifications are, and as long as you meet those, you'll end up being approved. So that is the different certifications that we offer in the primary track. Of course, we have CWTS as well for sales professionals, telephone support, help desk support, those kinds of things. And even just as an entry-level certification for people who just want to grab that first certification, that's a little easier than CWNA. To put in perspective, CWNA in the class is a 5-day class. CWTS is a 2 or a 3-day class, depending on how the authorized learning center chooses to run it. And then, of course, we also have CWNT, which is a certified wireless network trainer, and those are people who are authorized to actually teach any of our other classes that we offer through the authorized learning centers. So now let's talk about the agenda. The agenda is exactly the same as it was last month, but the focus is just a little different. Last month, we really talked about just the causes and really didn't get into detail about how do we figure out what's actually causing these problems, which is what we're going to focus on in our 25 or 30 minutes together today. So the performance problems, interference, congestion, and low data rates that we talked about last month, we're going to be addressing those again. And then connection problems, can't connect to Wi-Fi, or maybe they're connected to Wi-Fi but cannot connect to network resources. So we'll go through these same 5 things, but again, we're shifting our focus to causes. So when it comes to interference, I guess you could really put it into 3 basic categories of interference: Wi-Fi, non-Wi-Fi, and incidental. So Wi-Fi means other 802.11 networks that are interfering with your network, or your network interfering with itself. Okay, so this is what we typically call co-channel and adjacent channel interference. So this is where you have either other wireless networks that your neighbors are running, or wireless APs that you're running that are simply not configured well. There's a common move today, for example, to implement more APs for greater density and more capacity in each basic service area or in each cell. Well, we can certainly do that, but you have to keep in mind that as you implement more APs, you have to reduce the output power of those APs to avoid co-channel interference, and for that matter, to avoid adjacent channel interference. But even co-channel interference, we have to make sure we're reducing the output power significantly to accommodate for that. Even when we do that, it is important to remember that the client devices do not have their output power adjusted. That is to say, when you build a high-density network, you don't have the luxury of telling all of the people that bring in a device, hey, before you can use my network, you have to lower the output power on your client device. We really don't get the luxury to do that. And there are many laptops that have output power levels at the same or some even above that of access points. And so that laptop, for example, could be causing co-channel interference for other APs. Now, the good news is we know statistically the majority of wireless LAN traffic is downlink. So think of it like this. When you subscribe to high-speed internet on your home network, you've probably noticed that you have about 10% up of what you have down, maybe 20 or 25% if you're lucky. But the point is your uplink is slower than your downlink. Now, there's not some technical constraint that makes it where there's no possible way that they could give you an equal uplink to your downlink. Certainly that can be acquired, it can be purchased. But the issue is that you really don't need it in most cases. For example, if you're watching a movie on some internet site like Netflix or Hulu or YouTube videos or whatever, the vast majority of that traffic is coming to you, and very little is going from you up to the Netflix, Hulu, or YouTube servers. And so therefore, the majority of just general network traffic that is generated by a client is what it is requesting to come down to it, and not so much those small requests to get it. So if you think of it, for example, to download a web page, you're downloading an HTML file and you're downloading several images, right? Well, each one of those images is an individual HTTP GET request, but the GET request is very tiny, maybe 2 to 3% the size of some of the images, certainly probably 5 to 10% the size of many of the images. And so even with the web page with all of that back and forth, still the vast majority of traffic is downstream. And so this is common. It's common behavior of network traffic. Therefore, even though the clients have higher output power than the APs, they do not create as much co-channel interference as the APs do. There are more frames sent by APs than any other device in a typical basic service set. And therefore, when we lower the power of the AP, we greatly reduce co-channel interference. We do not obliterate it because the clients can cause co-channel interference as well. Remember, co-channel interference simply means that your device that wishes to communicate cannot because it has heard an 802.11 frame at a signal strength where it must acknowledge it and keep silent. So that is part of CSMA-CA, Carrier Sense Multiple Access Collision Avoidance, the fundamental communication mechanism of wireless networks. And so because of that, we have this co-channel interference, or what many call co-channel contention. I actually like that better because it's not interference in that there's RF energy being generated and we don't know what it is kind of interference, but it's the kind of interference that we know what it is, and it's the normal behavior of wireless LANs. So all of that to say that Wi-Fi is one kind of interference. Another is non-Wi-Fi. And I have an image here of an HDMI wireless device. So what you do here is you connect one of these to a computer or a video system of some sort. It could be a gaming console, it could be a Blu-ray player, but you connect it to some video source. And then you connect the other one to a TV or a projector, for example. And then what these two things do is they send the video signal using 5 gigahertz between them. Now, I've used one of these, not this exact one, but a device like this, in training classes for years now to demonstrate non-Wi-Fi interference, because the one that I have actually, it typically uses channel, I want to say it's 165, but anyway, it uses one of those channels if it's clear. If it's not clear, it'll use one of the other channels. But the point is, the utilization is practically 100%. So if you were to look at it with a spectrum analyzer, you would see the duty cycle at about 100%. You would see that it's just continually streaming, and that's even if you're not sending any video through it. In other words, you can power both of these two devices on, they'll gain a connection with each other, and they're still using 100% of that channel. So this is an example of a non-Wi-Fi device. Now you might say, well, surely, Tom, those are only used in the consumer space. Actually, they're not. They're used a lot in conference rooms. They're used in the educational space. They are used in many meeting type areas. So churches, all of these kinds of things will often use these to get a video signal to a projector without having to run a cable. And obviously you just lost one of your 5 gigahertz channels. And you've lost, in most cases with these devices, one of the 5 gigahertz channels that is not concerned with DFS compliance. And so it's not like it just uses one of the DFS compliant channels, and if it detects radar, it'll move around. No, because it doesn't want to have to detect radar, it uses one of the 5 gigahertz channels where it doesn't have to. And so you're losing one of your 5 gigahertz channels. And this is why I say 5 gigahertz is clean right now. But what are we doing? We're motivating everybody. We're encouraging everybody. Use 5 gigahertz. Our mobile phones are coming out with it. Our laptops are coming out with it. And we're getting more and more devices. So 5 gigahertz is destined for congestion down the road. And that's one of the reasons why they want to give us more frequency space there. Because if we don't get it, and later chipsets that come out in the future do not support extra frequencies or channels, then we're going to be back in a similar problem we've been in 2.4 gigahertz for some time. The other kind of interference is incidental, and I've got a microwave oven here to represent this. The microwave oven is not trying to send a signal. It's not trying to modulate data bits onto the radio frequency. Instead, it's usually on about a 50% duty cycle. You'll see that it's on and then it's off and then it's on and then it's off, about 50% duty cycle, and it can eat up nearly all of the 2.4 gigahertz spectrum. 2.4 gigahertz waves are absorbed very well by water, and therefore they're used in microwave ovens. And so microwave ovens can definitely cause a degrading in performance by 50 to 70% for people that are very close by to that microwave oven. Now, thankfully, it's a low output power, not because there's low power in the oven, but because the oven is kind of built like a Faraday cage, and so it keeps as much of the RF energy in as possible, but much of it does still leak out, and for those that are near it, it could cause problems. So these are your 3 kinds. When you're looking for interference, you're generally looking for one of these 3 kinds of interference: Wi-Fi, non-Wi-Fi, and incidental. So how do we locate interference? Well, there are really 2 primary tools, and they are spectrum analyzers and protocol analyzers. Now, a spectrum analyzer could be one that you run on a laptop computer with a USB adapter or some other kind of adapter, or it could be built into your access point that you have a spectrum analyzer. Now, the spectrum analyzer built into the access point in a high density environment is a little better because access points are pretty close together and they'll pretty well see anything that's out there because they're so close together. But when you have non-high density or medium density or even low density deployments where maybe you're putting in an AP every 50, even 80 feet, in that case, the spectrum analyzer in the AP may not do you a lot of good to view what's going on where the client is actually located. Now, the good news is spectrum analyzers are, well, spectrum analyzers. They're not constrained by the PHY. So, for example, if you have a spectrum analyzer, it doesn't matter if it's a VHT, that's 802.11ac, HT, 802.11n, OFDM, 802.11a, ERP, 802.11g, HRDSSS, 802.11b. It just doesn't matter what modulation and PHY layer is being used, because you're looking at the RF energy. Now, some of the spectrum analyzers will integrate with a Wi-Fi adapter to tell you a little bit about that 802.11 signal, but you can still see the RF energy without it. So I guess what I'm saying is, a lot of people are concerned getting protocol analyzers in the future to analyze 802.11 AC, especially Wave 2 with multi-user MIMO, protocol analyzers to do 802.11ax once it comes out, and then eventually AH, right? So we've got all of these thoughts of what's the future of protocol analysis. Well, those are valid thoughts, but spectrum analysis is spectrum analysis. And so we can look at the RF energy regardless of what 802.11 amendment-based PHY is actually being utilized. And so laptop spectrum analyzers are going to be very useful for a very long time to come, because we can take them closer and closer to very near the source of interference. Now, you can also locate interference in a protocol analyzer, but generally what you're looking at there is co-channel interference, because the protocol analyzer lets you see and report on all of the different access points that it sees and the signal strengths from those access points. So you can get an idea. So you might see an access point, but the signal strength might be extremely low. And if it's extremely low, then it may not be causing as much CCI. If it's, however, higher, say something like a good signal strength of 50, neg 50 to neg 65 dB or something like that, then you're probably going to be running into some major co-channel interference from that particular basic service area. So protocol analyzer, spectrum analyzer, use it to look for interference. Now, with the spectrum analyzer, you can locate non-Wi-Fi and incidental interferers. With the protocol analyzer, you could only locate Wi-Fi. With the spectrum analyzer, you could actually locate all three. So the key with the spectrum analyzer, when looking for a particular source of interference, is to move and look for greater strengths in that protocol analyzer signal as you're moving. If the strength is getting greater, then you're getting closer, right? If it's getting weaker, then you're getting farther away. Generally speaking, now obviously we have reflection and refraction and diffraction and scattering and all those wonderful behaviors of RF, right? So technically speaking, it's possible you could move 2 feet closer to the device, but be in a spot where the signal's not as strong. So it's not about necessarily micro movements when locating sources of interference. But many sources of interference are pretty easy to spot once you get to where the signal strength is pretty strong, if they're out in the open. So obviously something like a microwave oven is going to be obviously there on a shelf or in a cabinet. A video camera, something like that. These are going to be more noticeable. But then there are things that may not be as noticeable or as obvious to you, like a fluorescent light ballast that's causing problems. And maybe it's just generating enough RF energy to cause problems for a user that's right under it or something like that. Or an electric motor that might just happen to be generating incidental RF energy. So these are the kinds of things that can be a little harder to identify, but it is important to take a look at. The question about the blip on roughly channel 9 there from Howard. You know what, Howard? I'd love to tell you I know, but I don't know because I just grabbed this screenshot out of our archives. So I'm not exactly sure what that is of. It is not a capture that I've created myself. But you hit one on the head there. Zigbee is one of those devices that can cause interference for 802.11. And sometimes those can be a little harder to identify because they're not always visible out in the open. Sometimes they're inside of machinery in manufacturing environments and things like that. Okay, so let's talk about congestion. When it comes to congestion, the causes are overloaded APs. So we've got too many users, or devices is a better way to say it, connected to an access point. We have busy clients. That is, we have clients that are using throughput intensive applications. You really can't see it in my slide here, but I have a screenshot of, I don't know, I call it MuTorrent. Maybe it's mTorrent. I don't know. It's that torrent downloader application so many people like to use. And that's a perfect example of, at least on the downlink, a bandwidth intensive application. But keep in mind what an application like that does. Right after it's done downloading it, it makes it available for upload, right? And so it could very well cause some uplink congestion too, but this can cause congestion. So you've got one or two clients that are really using a lot of throughput. And then, of course, co-channel interference can cause congestion because of the simple arbitration that has to take place to gain access to the medium. And so congestion is caused by overloaded APs, busy clients, co-channel interference. These are your major causes, and there may be more. So how do we discover congestion? Well, there are a few things we can do. One, we can look at the association table on the access point to see how many clients are connected to it. I've seen times when you've got two access points in an area, and one of them may have 25, 26 stations associated, and then the other one only has 4 or 5 stations associated, while many of these stations associated with the one could be associated with the other. And sometimes that happens because of the wonderful sticky client problem we like to talk about. The signal strength may be just significantly different enough for most of those clients to choose the other. But the point is that if they couldn't associate with the one, then they would associate with the other. And so you may be able to, depending on your access point vendor, adjust the number of allowed associated stations to accommodate in that kind of scenario. You can also use tools like iPerf and Tamosoft Throughput and others so that you can test the throughput. That is to say, if you tested the throughput in that particular BSA at one point and it was acceptable, and you go back now and test it and it's not, then you do know you have a congestion problem, and you've got to find out why. Is it interference? Is it overloaded APs? Is it the fact that you've got a client that is doing more throughput than it should? That is to say, maybe it's not using business applications, but personal applications that are causing problems for all of the other users. So that's something that's important to look out for as well. Now, one of the things to keep in mind, by the way, and that's why I have it here on the screen, when you're looking for the source of congestion, and you're looking at interference, for example, one key thing is to look at utilization. And this is important when you consider even a non-Wi-Fi interferer, because if the non-Wi-Fi interferer is only utilizing 10% of the airtime, then your wireless LAN should still be able to function, and function pretty well, actually. But if that interferer is utilizing 70% of the airtime, obviously you're going to have very serious problems. And that's why I pointed out the HDMI wireless video adapter using nearly 100% of the airtime pretty much makes that channel unusable for Wi-Fi. And so that's just an example of a device where it has very high utilization. So not every quote-unquote interferer you find is necessarily going to be a problem for the performance of your network, because they may have very low utilization. But if they have medium to high utilization, that's when you're going to see they really begin to impact your wireless LAN. So next, we talked about low data rates. The causes of low data rates are poor signal quality. So this can be because you're too far from the AP. You're in an environment that has created a space with low RF signal, even though you're close to the AP. So in other words, it could be that there are some kind of walls around the space that you're in, special walls with special lining in them, like lead walls or something like that. So it's not just about physical distance. A good way to think of it is RF distance. And if you're just thinking of RF distance, what you're really looking at is signal strength, right? So you could be very close to the AP on physical distance, but your signal strength is weak. So we could say signal-wise, you're far from the AP. But generally what we would say is it's the environment causing the signal to degrade to such a point where you're unable to get the higher data rates. Remember, getting a higher data rate means getting better SNR. So if your signal-to-noise ratio is low, you're not going to have a higher data rate. If your signal-to-noise ratio is high, you're going to have a better data rate. So that's the key there. So if the signal itself is weak at the location, then you're going to have a noise floor, and the difference between that signal and noise floor is your SNR. If you have an SNR of 10 or 15 dB, you're going to find yourself at those lower data rates. If you have an SNR of 20, 25, certainly 25 or higher dB, you're going to be able to hit some of those higher data rates. Of course, the noise floor is a factor in that equation, and we see it here in a real-time fast Fourier transform screen. Also, low data rates can be caused by a configuration error, meaning that you're allowing them. So we'll talk about that here. So how do we discover them? Well, you can discover your data rate easily for an individual client. So we're looking here at the Wi-Fi status just on a standard Windows 8 computer, still the same dialog box in Windows 10. And you can see this one happens to be connected at 216.5 megabits per second. So that just happens to be the connection for this particular device. You can also see it in a protocol analyzer, but the benefit there is you can see it for many more devices. So you can actually get a picture of an entire basic service area, all of the stations that are connected to that basic service area, and then an average data rate if that's what you want to see, or you can just see the lowest, say, 2 data rates or something of that sort. So this can allow you to identify maybe where there are configuration errors. For example, you may have intended to disable 6 megabits per second in 5 gigahertz. And you use your protocol analyzer and you see that you've got 3 clients that are connected at 6 megabits per second. Well, that could mean that you have not configured that AP properly. So somewhere you failed to make 6 megabits per second unsupported. So basically, if 6 megabits per second is unsupported, then what you're saying is they cannot associate at that data rate. It's really that simple. Now, we can configure it in our devices. You can configure it if you're using RRM. You can configure it with transmit power control. You can just configure it manually, but nearly all, certainly all enterprise APs and even many consumer APs, depending on the firmware on them, will now let you configure the data rates that you will allow. So you may want to disable some of those lower data rates. There are some arguments against disabling data rates, but the general consensus is that disabling the lower data rates can help improve the overall throughput of a particular basic service area. Now, cannot connect to Wi-Fi then. The causes we talked about last month: interference, misconfiguration, security settings, or maybe a firmware problem. So let's talk a little bit about these. To troubleshoot your connection problems, take a look at the DHCP server to see if the pool is exhausted. So sometimes it's a simple factor of the client cannot get a DHCP configuration set. And the reason I point this out is what I told you last month. Users simply say, hey, I have no connection to the wireless network. Well, they actually do, but they can't get a DHCP configuration set because the pool is depleted. So check your DHCP server, make sure that it has sufficient IP addresses available. And then the other thing is to look at your security settings. Now, more often than not, with security settings, if we're using WPA2 Enterprise, we're going to find that the clients are configured appropriately because they're configured by someone in IT. So more often than not, we're okay. More often when you have security mismatches, it's with WPA2 Personal. And you'll notice I'm not even mentioning WPA. That's because I wish the world would move away from it. But maybe you're still using that too. But the point is, if you're using the personal version, meaning you have a pre-shared key, then that's a common thing. The wrong key is entered and they can't get onto the wireless network. And one common issue that you'll run into there is a company may be using WPA2 Personal, and they may have multiple locations, and they may have a different pre-shared key at each location, but the same SSID. So the user connects to that SSID at one location and everything's fine. They go to the other location and they can't get on. And they don't even think to change the pre-shared key because it's just there. It works. The SSID is configured. So that's something to watch out for. That's not uncommon. It's probably better to have different SSIDs at each location. Maybe some little 3-number value at the end of the SSID to indicate the location. If you have a master location and you want it to say My Big Company as the SSID name, and just that at that big location, fine. But then at all the small locations, you might say My Big Company -1 or just 1, or My Big Company 2, or what have you. Something to differentiate so that those stations can have the different pre-shared keys configured. So that's not an uncommon issue that you run into there. And then, of course, firmware upgrades. I believe I mentioned it last month, and you've probably heard there was a time when I believe it was Windows 8 was first released. It supported 802.11w out of the box, and so there were some problems connecting to some Cisco APs. And it wasn't a problem with Windows 8. The firmware, or the 802.11w was implemented properly in Windows 8. It was a problem with the firmware on the Cisco AP, so it had to be updated for those clients to be able to connect. So those are important to keep in mind. Question has come in some cases, would a high level of co-channel contention appear to be a data rate problem or be misperceived as a data rate problem before proper troubleshooting? Yeah, I think you could see that because, the symptom of co-channel contention is going to be slower throughput, right? Because we're having to wait longer to transmit frames because of the other service area, the other basic service area that is causing the CCI or the CCC. And so, yes, it would give that same type of symptom, but thankfully the troubleshooting is really quick, and even over the phone you can step them through, go to this dialog, tell me what it says your data rate is. If they have a high data rate, getting poor performance, then there's probably one of the other congestion problems that we talked about going on. Okay, the final thing to talk about here to wrap up our time together today then is cannot connect to resources. And you know what? This is a really typical rundown, and some of these things we're going to be looking at troubleshooting them next month when we talk about general network troubleshooting. When you can't connect to resources, and we're talking about file servers or email servers or web servers or application servers, these kinds of things. When you're in these situations, it can be any of these causes. Misconfiguration, so the client application may not be configured right, or the server may not be configured right. ACL blockage, so maybe you've implemented some new protocol and the ACLs in your routing infrastructure do not allow for it, so you have to go back in and reconfigure your ACLs. Service may be down on the server or the virtual machine or whatever it is, or the service is overloaded. It could be a routing error. So maybe one of the routers is misconfigured. There are times when people will, for example, configure load balancing out two interfaces on a router to two different switches. And it may be that the routing is okay, but one of the switches has broken its link back to a service or something. And so those kinds of issues can occur. DNS problems where we're unable to resolve a domain name in order to accomplish accessing the resource. A VLAN problem. The user may somehow be being placed in a VLAN that doesn't have access to the resource. And so, a lot of times you spend all this time troubleshooting. They can't access, say, the corporate email server, right? And so you go in and you think, well, I wonder what it is. You'll reset the access point. You'll go into the wireless LAN controller and look at the logs, and you disconnect them and reconnect them to the wireless network, and you renew their IP lease, and you do all of these things only to find out that they're connecting to the guest wireless LAN, and it's the wrong VLAN. So the point is that some of the basic things that you have to just watch out for in these areas, and of course, general application problems as well. Well, that's all we have scheduled to cover in the presentation today. So we'll take some time here for any questions that you might have. And let me just say as well that Wi-Fi Trek is coming again this year. We're going to two places. We'll be in Prague in June, and we'll be in New Orleans in September. So you'll want to watch the website for those dates and try to come to one in your region if you can at all. It's always a good time. A lot of presenters, experts from the Wi-Fi industry talking to you about the latest and greatest in technology. Most likely I'll be presenting on 802.11ax and 802.11ah at both of the conferences this year, so you'll want to be sure to be there to catch that. But I'll open it up to any questions that you might have. If you don't have questions, let me just thank you for attending the presentation today, and I look forward to you being with us again in future months. Do watch for the newsletter and the schedule of upcoming webinars, and always know that they're archived at CWNP TV on YouTube.